Hello everyone. I will attempt to edit the stream replay to get a shorter video to upload later on. So these are called rotors. The shape rotating inside the other shape touches all sides of the outer shape at all times. If you do some hunting on Google, you'll realize two things very quickly. For number one, there actually are practical applications for things like this. There are lots of like gear mechanisms or whatever that rely on this type of thing. This is a Soviet film projector whose motion depends on the fact that this Reuleaux triangle is rotating inside a square, right? Which is kind of interesting. These are also curves of constant width. So as you rotate them, I was actually going to show the bikes. I included a link to the bikes in my description. So, you know, this is a nice person who is of course riding a bike. And the wheels of the bike are shaped like these Reuleaux triangles. And the reason that this works is, because this shape, as it rotates, it maintains a constant width, essentially, which is really, really special. And so I saw this and I immediately thought, I want one. You know, I want to make a shape like this. That'd be so much fun. Well, there's one approach that people can take, and this is a very kind of common approach. So the way you make Reuleaux triangles is, you know, you take a circle here. Imagine this drawing is symmetric. You know, use your use your imagination and pretend this drawing is symmetric. And basically, if you have 3 circles at a certain distance from each other, then the intersection of all 3 circles will give you precisely this triangle that works so well over here. Will precisely give you a Reuleaux triangle. I wanted to contribute something to this, and I kind of wanted to do something original. It's just something that was my own idea. Now, of course, just because it's my own idea, I make no claims that someone else has not come up with this idea before. So, you know, I feel like most ideas people have already come up with. Here's what I'm gonna do. So you start with the shape that you want to rotate inside. You know, let's say you have a square. You take a bunch of points inside this square, start rotating them inside the square. So rotate this collection of points as a unit inside the square. You just get rid of the ones that eventually fall out of the square and see what's left over. That's what I thought last night, that this would be like a fun thing to do. The first thing that I realized very quickly is that you're gonna have to rotate this shape on kind of 2 axes of rotation. So you rotate the entire shape around the origin, let's say. Okay? And then you need to pick a center. So you have to pick a point that's a certain distance away from the origin. And then you rotate again along this point. So this entire collection of points is being rotated about a curve that looks something like this. You know, it'll look something along these lines. Depending on what you set the parameters to. Of course, there's a lot of parameters to tweak here, but let's just see how it goes. This is my initial collection of points. I already started coloring red the ones that are lying outside of the triangle. And then as I hit next, the points that are colored red are canceled. So if any of the white points ever dips outside of the triangle, it's basically done for. Okay, so you can just keep doing this over and over again, and you wait to see what happens. So of course the strategy is that if you only preserve the points that are always inside the triangle, right? If you only preserve the points that are inside the triangle, my idea was you should be able to get one of these shapes at the end of it all, like one of these types of shapes. Not a circle, right? A circle can clearly rotate inside here, right? Without causing too much trouble. But I'm interested in shapes that can rotate inside other shapes, touching all of the edges, right? And so this is my plan of attack to do that. So just keep hitting next over and over again. So it kind of seems like most of the points are getting colored red, you know, most of the points are leaving this triangle at some point. The proportion of the speeds. So all you need to worry about when you do this is the proportion of the speeds at which things are rotating out, like along the the origin, and the speed at which it's rotating along the second point. And so what you're seeing now is this collection of points rotating inside of a triangle, and the speeds are set to be the same. Okay, so there's a couple of parameters here. There's a radius here, right? There's a radius here that this is the distance between kind of this point and this point over here. There's a radius, and then you have to worry about the ratio of the two speeds, like the ratio of the speed of rotation along this central point and this other point. Unfortunately, at the 1-to-1 ratio, you just get a circle. You get a circle, and it does not touch the sides of the triangle at all times. That should make sense to you that for most occurrences of this setup, you will get a circle, right? So like if you take this collection of points and you rotate it around, I mean, you can imagine you have like a bunch of like marbles on a square table, right? Actually, that's actually not a bad visualization. Actually, someone should make that visualization. I feel like it would be very cool, actually. But imagine you have like a whole bunch of marbles on a square table, or a triangular table in that case. And then you start doing this with your set of marbles, you know? You start doing this motion with your set of marbles, right? And then at some point, you know, a lot of the marbles will start falling off the table, and what's the shape of the set of marbles that will be left over? Well, the shape of the set of marbles that'll be left over, in this case at least, is going to be a circle. So I did, some experimentation here, trying to get this to work, and I kept getting a circle over and over again. And then I thought about it for a little bit, and I realized, I slowly started to realize what the ratios of these speeds need to be. So it turns out that if the speed around the central axis of these marbles is like 1. Let's just set it to 1, okay? And let's say the number of sides of your table is n. Then if you make the speed around the second point negative n over n plus or minus 1, it seems like you always get something interesting happening over here. Let me prove my point. So here the speed is set to 1 and 1. So the speed around the central, like the origin, is 1, and the speed around the secondary axis is also 1. But this triangle has 3 sides. Let me try negative 3 over 4 for the speed on the other point. And let's just see what happens here. Okay. And don't worry, I have a smoother animations as well. I just want to illustrate the point. So this collection of points is rotating about 2 axes. I set the speeds a certain way. That's interesting, right? You're not getting a circle anymore, are you? You get it looks like, you know, a 4-sided shape, or like at least an approximation of a 4-sided shape if you rotate all of these points around, right? That's interesting, looks like. Also, for example, let's try it with a different number of sides. So let's say we do maybe 4 sides and do negative 4 over 5. What do you know? This time you get a pentagon, or at least a pentagon-looking thing. So it seems like, after much effort, this strategy does bear fruit. You do get shapes like this. So we were able to construct, so instead of a Reuleaux triangle rotating inside a square, we were able to construct kind of a pentagon rotating inside a square and touching all sides of the square at all times. Here, this has the same setup as the start. The speed around the central axis and the speed around the secondary axis are the same, so we should wind up with a circle. So, okay, it got rid of a lot of points right at the start. Like, most of these points aren't on the table to begin with, So, and you just keep going. And you can see as points fall off the table, they kind of get shaved off, right? And so the shape, you know, starts to look more and more and more like a circle, which is what we got in the original simulation when the speed on the central axis matched the speed in the secondary axis, right? But now let's do what we did the second time. Actually, let's try to get a Reuleaux triangle now. So let's set S to be -4/3, which is what I figured out would work to give you the Reuleaux triangle. And let's just see what happens. Okay. So immediately, most of the points fall right off the table. Hey, hey, there it is. How nice, how nice. Just a little Reuleaux triangle for all of us, huh? That's pretty cool, right? Man, I cannot tell you how happy I was when this first worked, because it did not work for a long time, but there it is. You really do get a Reuleaux triangle. Okay, now I'm not drawing the points anymore. So this is a ratio of -4/5. I wanted to try different side lengths and different ratios and see what kind of shapes we would get. So since you asked for a pentagon, I want to do a pentagon. Let's do a pentagon with, let's shoot for a quadrilateral inside of a pentagon. Let's see what happens. And, hey, not bad. Not bad. So I can try to sort of sharpen. So this is a very kind of smooth quadrilateral that's sitting inside of a pentagon over here. And you know what? It looks quite nice. I like the appearance of this. It's quite nice. One thing you can mess around with is you can really like bump up the diameter of this inner rotating circle. Oh, sorry, not the radius. So I'm kind of curious what would happen if I did that. Hopefully, like something really wild and crazy is gonna happen. Okay, so to answer your question, Ken, it looks like increasing the radius sharpens the corners, right? But I feel like if you keep increasing the radius, you'll get to a point where it no longer touches the sides of the shape anymore, right? So I'm kind of curious. I want to see how far I can take this. So let's try 0.2. Everything is scaled to 1, so 0.2 is, yeah. So if you set the radius too high, it no longer touches all of the sides of the shape. Almost there. You know what? I think, can you try pentagon inside of a pentagon? Unfortunately, nothing happens. If you do so for example, if you do a pentagon inside of a pentagon, this is what happens. Here, let me show you. Pentagon inside of a pentagon would be this. So that's what happens. Okay, so hopefully that answers your question. Unfortunately, nothing, nothing exciting happens if you try the same-sided shape inside the same shape. It's a good question. I tried it too. I had to try it to find out what would happen, and I found out that this is what happens. Like, I don't know. Let's try a octagon in a heptagon. That's kind of, I feel like that'd be kind of cool. So this is an octagon in a heptagon. Okay, I need to lower the radius. Let's go with 0.05 again. And what do you know? That kind of works. Yeah. So let's just do one with a triangle really quick, because I think triangles are fun. Let's do -3/2. So it turns out you get an oval if you do a inside a triangle. Just kind of neat, right? Okay, so what if we held the oval still and rotated the triangle around it? Okay, that was the next thing that I wanted to experiment with, like holding the internal shape still, rotating the polygon, and then seeing the path traced out by the outer points. Interesting. Look at that. How about that? So yeah, I wasn't expecting this, but it's really interesting. But let me change the sides to 5 and this to -5/4. No, that still works. Let's do 6 and 5. Interesting. But I think that's it out of me. So I hope you guys had a wonderful time. Thank you to everyone that decided to show up. I really appreciate it. Peace.